All right, welcome to your first lesson on electromagnetism. So the first question is, sound cannot travel in a vacuum, so that means that there's no air. Can magnetism, and what about electric charge? So the answer is yes. Magnets will work in space. And that's because they're exerting a force around on the stuff around them. And what about electric charge? So yes, magnets will work, and so will electric charges. And so the first part of the video was just about magnets and how people noticed magnetic fields and things like that. So what I have here is just a container, a square container that has iron filings in it. So there's just iron filings in a liquid. So if I shake it a little bit, you can see the iron filings. They're the black things there that are floating in the liquid. So here they are, they're just all floating in a random pattern. But if I take a magnet, and so this magnet is north on the red side and south on the silver side, and I put it into the center of this container, has a hole in it so that I can insert the magnet, what you will start to see, and I'm going to try to get this without a glare on it, what you will hopefully start to see is that, see at the ends here, the iron filings are sort of arranging themselves in a pattern. And what I'm going to do is I'm going to shake the iron filings so that they fall down. And that way you can really start to see how they're attracted to the ends of the magnet, but then they are sort of forming themselves into these lines that you can see on both sides. So you can see that it's in a circular sort of pattern. The circles are getting bigger out here, and it's circular like that. So if I were to move the magnet down and just kind of shake the iron filings again, actually I took the magnet out just to sort of release the filings from where they were. I'm just going to put it back in there. And you can see that the iron filings are being attracted. Iron is magnetic, so it's being attracted to the magnet. And then once again, as you're looking at it, you'll see that it starts to basically form these lines around the magnet. So you can see as the iron filings are falling, they're making this sort of circular pattern, and it's three-dimensional. So if I turn the magnet to another side, you can still see that circular sort of pattern that's happening all around the magnet and then out from the ends. You can also see that lots of iron filings are going to the ends here, and there's less in the middle. That's because magnets are strongest at the ends of the magnet. So we'll draw magnetic fields a different day, but that just kind of gives you an idea of what a magnetic field might look like. So draw with details the device that Alessandro Volta made. So what we've got is we've got coins, two different coins being stacked together. And so hopefully you have this drawn out in your notes. And the important thing is that whatever your top coin is has to be different from your bottom one. So these were copper and silver, and the atomic symbol for silver is Ag, so copper and silver. And what he did is he connected both ends, and with wires, so he added wires. And when he connected the ends, he got a spark. And this was the first battery. And what that did, when we had a battery, was allows for the control of current flow so that, basically we could prove some experiments with electricity. So before this, we only had static electricity, which we talked about at the beginning of our electricity unit, where you got a spark and then it was done and it was gone. But now we have a flow of electricity, which allowed for more experimentation. So Hans Christian Ørsted did an experiment in 1819. He hoped to show that electricity and magnetism were not related. And he was actually a teacher, sort of like a professor, and he went into this lecture hall with all of his students to try to prove once and for all that electricity and magnetism were not related. So what did he do? He took a wire and he put a compass by it. And when we draw a compass, we draw it as a little triangle, two triangles. The dark side usually represents the north, and the south side represents the south, the light side. So he took a wire and he put a compass by it, and then he turned on the electricity, so turn on the current. So he put the wire perpendicular to the compass, and that's shown. I actually did this experiment, and so that's shown in the picture. And then he turned the current on, and what he noticed was nothing. And so as a teacher, he thought, hey, this is going really well. My experiment is going to work out. So this was the first trial. So the compass was at 90 degrees and didn't move. And so he thought, hey, this is good. But then he did another trial. And on this trial, he had the compass being parallel to the wire. And again, all the pictures here are coming up one at a time. So he set it up so that it was along the compass at first. And then he turned on the current, and the needle jumped to perpendicular. So the second trial was that the compass was along the wire and moved to be 90 degrees. So what he did was he proved the exact opposite. He proved that electricity and magnetism are related. And so that was in the early 1800s, and it took a long time before this became really useful, actually, for anybody. But all right. So the video describes a left-hand rule, but we are going to use our right hand for a right-hand rule for conventional current flow. So if the electrons are flowing this way, then the conventional current is flowing the other way. And the reason for that is because when people were first studying electricity, they thought that it was the positive charges that were moving. And we eventually learned that it was the negative charges. But while that was happening, math and science sort of developed together, and ended up making the right-hand rules, and then we just kind of stuck with them in physics. Even though we know that the electrons are moving now, we are going to still use our right-hand rules. So whichever direction the current is flowing, the current is your thumb, and the magnetic field is your fingers. So around a wire, the thumb gives you the current, and the fingers give you the circular magnetic field. So around a wire, the magnetic field is circular. And so if you were to, for example, take your pen and kind of imitate this, the thumb being your current, your fingers are wrapping around, if you were to look at it in a counterclockwise direction. So the magnetic field around this wire is going that way. So it's creating a magnetic field around the wire, and we draw them out as circles. So if we were to have a wire going this way, then what you would do is you would take your pen, as shown in the diagram, in the photo, and just imagine that your pen is the wire, and your thumb, as well as the tip of your pen, is pointing in the direction. And what you should be able to see in this photo is that your fingers are going up at the back, and they're coming over and down at the front. So the magnetic field around this wire is going up at the back and down at the front. And you should make sure that you put a break in this loop around your wire. If the current was going the other direction, if our current was going that way, and again, we would take our pen and we would aim our thumb in the direction that the wire is pointing. And now if you were to look at it, you would think, oh, my fingers are going up at the front, and they're going down at the back. And so it's going in the clockwise sort of direction, whereas this one's going in a kind of a counterclockwise direction. So this is what you would do if the wire was straight. But what about if you were looking at the wire? So when you have like a wire cross section, when you have a dot in the wire, you should imagine that the current is coming towards you. So if the tip of my pen represents the current, it would be like it was sitting upwards on the paper like this. And if the tip of my pen represents the current going into the page, then we draw it as an X going down. Okay, so tip of the pen coming up. So then you would set up the pen sort of so that it's looking at you. So your thumb is pointing towards you. And you can see here that my fingers are curling around in a counterclockwise direction. So around this wire, the magnetic field is going this way. And if I was to put my thumb pointing down into the page, then you can see that my fingers are curling around this way. And so this wire, the magnetic field is going clockwise like that. So this is the side view for a straight wire. And then this is the sort of the top view, or a cross section view, all using the right hand rule number 1, where your thumb is pointing in the direction of the current and your fingers are the magnetic field. Now, when you end up with a coiled wire, basically the right hand rule number 2 is the opposite, sort of the right hand number 1. So the fingers is the current, and the thumb is going to point north. So on this, just imagine every finger is like a coil of wire for your diagram. So if all of the fingers are coming up at the back and down at the front, that would look like this. So down at the front, each coil of wire. Then your magnetic north is going to end up over here. And if all your fingers, if you were to grab the wires so that all of your fingers are going up at the front, like is shown in our diagram. So just imagine all your fingers like the wires. So the current is going kind of up and over, up and over, up and over. Then your magnetic north. So the inside of this thing basically starts to act like a big magnet where you have north and south. And that's right hand rule number 2.